Our understanding of the universe has undergone profound transformations throughout history. From the earliest days of human curiosity, we have gazed at the stars and wondered about our place in the cosmos. Ancient civilizations crafted myths and legends to explain the celestial patterns they observed, laying the groundwork for future scientific inquiry. From the Earth-centered model of the ancients to the heliocentric revolution sparked by Copernicus, each new discovery has reshaped our view of the universe. The shift from a geocentric to a heliocentric model was not just a change in perspective, but a monumental leap in our understanding of celestial mechanics. Humanity's quest to comprehend the cosmos has been marked by paradigm shifts. The invention of the telescope opened up new vistas, revealing a universe far more complex and vast than previously imagined. Each breakthrough has brought us closer to understanding the fundamental nature of reality. Today, we stand at the cusp of another such revolution, one that challenges the very fabric of our understanding. String theory. This groundbreaking theory proposes a radical new way of looking at the universe, one that could potentially unify all known forces and particles into a single, coherent framework. Imagine a world not built from tiny, indivisible particles, but from minuscule, vibrating strings. These strings, though incredibly small, hold the key to unlocking the mysteries of the universe. They vibrate at different frequencies, much like the strings of a musical instrument, creating the fundamental particles that make up everything around us. This is the essence of string theory, a theoretical framework that replaces the point-like particles of traditional physics with one-dimensional extended objects called strings. These strings are so small that they are currently beyond the reach of our most advanced scientific instruments. Yet they offer a tantalizing glimpse into the underlying structure of reality. These strings, far smaller than anything observable with current technology, are believed to be the fundamental building blocks of all matter and forces in the universe. By understanding their vibrations, we can begin to piece together the puzzle of how the universe operates on the most fundamental level. Just as the strings of a violin vibrate at different frequencies to produce a variety of musical notes, the vibrations of these fundamental strings give rise to the diverse particles and forces we observe in nature. Each type of particle corresponds to a different vibrational pattern, creating the rich tapestry of matter and energy that fills the cosmos. The vibrations of these strings are not random, but follow precise mathematical rules, offering a new way to understand the interactions between particles and forces. This elegant concept has the potential to unify all of physics, weaving together the disparate threads of our understanding into a single cohesive tapestry. This elegant concept has the potential to unify all of physics, weaving together the disparate threads of our understanding into a single, cohesive tapestry. As we continue to explore and refine string theory, we may one day unlock the ultimate secrets of the universe, revealing a harmonious and interconnected reality that transcends our current understanding. For centuries, physicists have sought to understand the universe in terms of fundamental, indivisible particles. The quest to uncover the smallest building blocks of matter has driven scientific inquiry for generations. From atoms to electrons, quarks to neutrinos, each discovery has brought us closer to the building blocks of reality. These particles, once thought to be the ultimate constituents of matter, have revealed a complex and fascinating subatomic world. Yet, a glaring inconsistency remained: the incompatibility of general relativity, the theory governing the large-scale structure of the universe, and quantum mechanics, the realm of the very small. This fundamental discord has puzzled scientists and has been a major obstacle in the quest for a unified theory of everything. String theory offers a radical departure from this particle-based paradigm. It suggests a new way of looking at the universe, one that could potentially reconcile the differences between general relativity and quantum mechanics. Instead of point-like particles, it proposes that everything in the universe is composed of these tiny one-dimensional strings. These strings are the fundamental building blocks, replacing the traditional notion of particles. These strings, far thinner than even the smallest subatomic particle, vibrate at different frequencies, much like the strings of a musical instrument. The different modes of vibration give rise to the various particles and forces we observe in the universe. These vibrations, encoded in the fabric of space-time itself, determine the properties of the particles we observe. The way a string vibrates dictates whether it manifests as an electron, a quark, or even a force-carrying particle like a photon. An electron, for example, is no longer a point-like entity, but a manifestation of a particular vibrational mode of a string. This perspective transforms our understanding of what particles are and how they interact. Similarly, the fundamental forces of nature, such as gravity and electromagnetism, are also thought to arise from the interactions of these vibrating strings. The interactions between different vibrational modes of strings could explain the forces that govern the universe, potentially unifying all known forces under a single theoretical framework. The implications of string theory are profound, offering a new lens through which to view the cosmos. It not only aims to unify the forces of nature, but also provides insights into the very fabric of reality. As researchers continue to explore and refine this theory, we move closer to understanding the true essence of the universe. The journey of discovery is far from over, but with string theory, we may be on the brink of a new era in physics, one that could finally reveal the ultimate nature of the cosmos and our place within it. The seeds of string theory were sown in the late 1960s, with Gabriele Veneziano's attempt to describe the strong nuclear force, which binds quarks together within atomic nuclei. His work unexpectedly led to a mathematical framework that could potentially describe all fundamental forces, hinting at a deeper, unifying principle at play. However, it was the realization that string theory naturally incorporated gravitons, the hypothetical particles responsible for gravity, that truly ignited the field. This groundbreaking discovery, pioneered by physicists like John Schwartz and Michael Green, propelled string theory to the forefront of theoretical physics. Over the following decades, the field blossomed, with contributions from brilliant minds like Edward Witten, whose work on superstring theory, a supersymmetric version of string theory, revolutionized the field. These pioneers, driven by an unyielding curiosity and a desire to unravel the deepest secrets of the universe, laid the foundation for what is arguably the most ambitious attempt to unify all of physics. Section 4. Unification, the Holy Grail of Physics. Since the time of Einstein, physicists have sought a unified theory of everything, a single framework that could seamlessly weave together all the fundamental forces of nature. This elusive theory, often dubbed the Holy Grail of Physics, has remained tantalizingly out of reach, a testament to the complexity of the universe we inhabit. String theory, with its elegant simplicity and potential to unify all forces, has emerged as a leading candidate for this coveted title. By replacing point-like particles with vibrating strings, string theory offers a framework in which gravity and quantum mechanics, two seemingly incompatible pillars of modern physics, can coexist harmoniously. This unification, if achieved, would represent a monumental leap in our understanding of the cosmos. It would provide a single, elegant framework to describe everything from the smallest subatomic particles to the largest structures in the universe, from the birth of black holes to the echo of the Big Bang. Section 5. Navigating the Labyrinth of Dimensions. One of the most intriguing and controversial aspects of string theory is its requirement for extraspatial dimensions. This concept challenges our conventional understanding of the universe and opens up a realm of possibilities that extend far beyond our everyday experiences. While we experience the world in three spatial dimensions, length, width, and height, and one dimension of time, string theory suggests that this is only a small part of a much larger picture. Our familiar three-dimensional space is just the tip of the iceberg. String theory suggests that our universe may harbor additional, hidden dimensions curled up at incredibly small scales. These dimensions are so minuscule that they are beyond the reach of our current observational tools, yet they could be fundamental to the fabric of reality. These extra dimensions, far too small to be detected by current technology, are thought to play a crucial role in the consistency of the theory and the properties of the particles and forces we observe. They might hold the key to unifying the forces of nature and explaining phenomena that remain mysterious. The extra dimensions are not just theoretical curiosities. They are integral to the mathematical framework of string theory, They influence the behavior of particles and the interactions between fundamental forces, potentially offering insights into the deepest questions of physics. Imagine a tightrope walker moving along a cable. To an observer from afar, the tightrope walker appears to be moving in only one dimension, along the length of the cable. To an observer from afar, the tightrope walker appears to be moving in only one dimension, along the length of the cable. However, this is a simplification of the true complexity of the walker's movement. However, the tightrope walker can also move in other, less obvious dimensions, such as swaying from side to side or balancing on the cable. These subtle movements are crucial for maintaining balance and ensuring a successful traversal of the rope. These movements, though subtle, are essential for the tightrope walker's stability and progress. Without the ability to move in these additional dimensions, the tightrope walker would be unable to maintain balance and would quickly fall. Similarly, the extra dimensions proposed by string theory, though hidden from our perception, may be crucial for the stability and consistency of the universe itself. They could provide the necessary framework that allows the universe to function as it does. These hidden dimensions might be the key to understanding the fundamental nature of reality. They could explain why the universe is structured the way it is and how the various forces and particles interact in the intricate dance of existence. As we continue to explore and develop new technologies, we may one day uncover evidence of these hidden dimensions, bringing us closer to a complete understanding of the cosmos.